All right, how y'all feeling? Pretty good? Everyone ready to go home and start mining, plugging their stuff in? Let's go. All right, so we have one more talk on the theme of Bitcoin mining, and then we're going to wrap the day off with Josh Doman talking about emulating covenants in trusted environments. Great. So everyone, please welcome Johnny9 to the stage. We're going to talk about Bitcoin mining firmware, tour of the ESP miner.
All right, thanks everyone. Yeah, so the goal of this is to try to kind of transfer some of the knowledge that I learned from this Bitaxe project. Before Bitaxe, this was all like a big mystery to me, and I've learned a ton, and I feel like mining firmware is complicated, but it's not too complicated. So I feel like I can try to explain it all so that you guys can all be mining experts too after this. So who am I? I am Johnny9. I am a software engineer in this area, a regular at Evan's BitDevs, and yeah, co-hosts. Yeah, but I definitely credit Evan and BitDevs for getting me into open source Bitcoin contributions. Over the last 2 years, I've contributed to the Bitcoin Core GUI project and also the Bitaxe firmware. As Scott mentioned, I guess this is my claim to fame. I was the first person to get Scott's invention fully working on its own by implementing the firmware on the device. And as I said before, Scott came here to BitDevs with his little device. I knew absolutely nothing about Bitcoin mining. So it's been an amazing learning experience, and I'm just proud to have sort of helped push this thing out the door and continue to be amazed by the impact it's having, both to like getting people interested in mining, but also the potential like big ideas. So it's really cool to hear that this is kind of working as a reference device for some of these big ideas. Okay, so let's start with this is what a Bitcoin miner looks like. It's a big metal box. You've probably seen these. These are the closed-sourced magical machines. But inside each one are these 4 basic components. There's a controller, there's hash boards, there's fans, and a power supply. And the controller, you can just think of it as like a Linux PC or a Raspberry Pi, kind of. And it's connected to the hash boards that has all the ASICs. Through a cable that has 3 types of communication: GPIO, I2C, and UART. The fans are connected through a cable and just have standard PWN, which controls the speed of the fans. It also reports back if the fans are working. And then the power supply also goes through I2C and allows the control board to change the voltage, the power that goes to the hash boards and the ASIC. So then we come to the Bitaxe, and it's fundamentally the same thing. You have the control board, you have the ASIC, which is your hash board, you have the controller for the fans, and then you have the bits that control the power that goes to the ASIC. So yeah, you can think of it as fundamentally the same thing, just kind of compressed into one little device. The controller itself is a microcontroller, and this I think is actually like the real cool invention of Scott here, is the fact that I don't know if he got lucky or what, but it's amazing that this thing can run an entire miner. And actually, yeah, it blows me away how powerful these things are. I actually didn't even know this, but you can almost just think of this as a processor that runs one program. And you can it's fast enough to mostly run any kind of general purpose program. And you don't even need to really consider too much about resources because it has a lot of resources. Anyways, so this is an ESP chip. ESP miner is built on the ESP IDF SDK. It uses FreeRTOS, and you can find the documentation for it. The documentation for these things is unbelievable. You'll learn so much just looking at those docs. But the thing to know, and the thing that's really unique about writing firmware, is you have all these pins that give you direct connections to the components. And here's the Bitaxe schematic. So that's the ESP chip over here. It's connected to the fan. This is an I2C bus, which is a shared bus. So over I2C, you have the power, the fans, and this is the ASIC. And over the ASIC, you have, or connecting to the ASIC, you have UART, you have a GPIO, that's the reset pin. So yeah, that's how it's all connected. You don't need to be a hardware expert, but with firmware, you just need to know how these things are connected so that you can have them talk to each other. That's the important part. So to go over that a little bit, if you haven't really done embedded stuff, you probably haven't messed with these sorts of things. But GPIO is like the most simple. It's a one-to-one connection, one pin, and you set it high and you set it low. And you can get input, you can set it output, or you can do both ways. This is generally used for LEDs, but it's also used for the reset pin on the ASIC. And most ASICs kind of have this. So you set it low to turn the ASIC off, and you set it high to reset it. So that'll clear out everything so you can start initializing it. I2C is a serial communication. It's like a master-slave thing. And so this will be a shared line with all your little components that set the voltage and the fans. The way this works is you transmit on the line. Since it's shared, you have an address that identifies which chip you're talking to. And these chips have registers, which are little areas of memory that you can read or write. That they'll have like, you'll be able to read the temperature, you'll be able to set voltage. So you're either reading the register or writing a register. And so you'll transmit with the address, the register you want to write to, and what data you want to write to on that chip. So here's an example directly from ESP Miner. This is setting the voltage. You can see the address of the sensor, the registers you're writing to, all the crazy conversion to change the voltage to whatever bytes it needs, and then it writes the I2C. So that's how voltage is set on one of these controllers. And so this is a data sheet. So if you start doing this, you'll eventually have to pull up a data sheet, but basically for all of these components, the manufacturers will provide a data sheet that describes all the register details and how to program them. In the age of LLMs, you can kind of just ask ChatGPT now, but to get confirmation, you go pull up a data sheet and you verify both the address of the device and all the register information. So that's how you'll know if you're programming it correctly. UART is, it has two pins. You have a send and a receive. Generally, it's between two devices, and it's very high speed. And this is the communication from the controller to the ASIC. And it needs to be high speed because you're potentially sending a bunch of work. And this is kind of what it looks like in the driver for the Antminer 1397. Write bytes, data, length. So yeah, and another point, because we're using this ESP IDF SDK, it does a lot of the heavy lifting for all of the signaling for these embedded protocols. So this is what, oh yeah, so for UART, the trick to it is that the ASIC and the controller need to know what the speed is of the channel so that they can correctly talk to each other. So you'll see this initialization. This sets up all of the configuration for the UART channel. How many data bits are in a frame, as well as the speed, and sets it up for you. So you'll see a lot of this, and a lot of initialization all across the ESP Miner. Now, the ASICs don't have a data sheet, and this is the problem with doing this open source mining stuff. But as Scott mentioned, there's been a lot of legendary heroes in this story. One of them was Nebula, the Frenchman. He did a ton of work, and you can find this under Scott. Basically created a data sheet for at least 2 of the Bitmain chips. And like the other chips, it has registers that you set to configure them. And it has a bunch of commands that you send over UART to tell it to do work. Along with that, one of the trickiest parts is for all of these ASICs, you have this huge initialization process. And a lot of this is still a mystery. There's a lot of magic bytes being sent here. But you do this once. And once you set it up, the chip is ready to go and ready for work. So in ESP Miner, there's a whole bunch of initialization code. It's kind of boring, but that's just the nature of this sort of firmware development. Is a lot of it is correctly configuring all of those pins on your controller so that you can communicate to all of the hardware devices that you need to control. Yeah, there's that. After that, once you initialize everything, you're ready to start the tasks. And so this is the list of tasks in ESP Miner. There's a power management task, 2 Stratum tasks, the ASIC task that manages the ASIC UART, and then there's a couple of monitoring tasks to collect information. Now this is task idea. You can just think of this as a thread. It's basically the same idea. But because it's a FreeRTOS embedded system, it doesn't have a kernel, so you have this idea of a task. And this is kind of what the power management task looks like. It loops, reads fans, voltage, and checks to see if the ASIC's overheating. Basically, this one's monitoring to make sure nothing blows up, and if it does, it shuts off the ASIC. Okay, so now we move over to the actual mining part. So once everything's initialized, you connect to your pool, which is run over Stratum. Stratum itself is a pretty simple JSON RPC protocol over TCP. What that means is you send and receive results in a JSON format. If you've done any kind of API development, you'll be familiar with parsing JSON. For JSON RPC specifically, all the messages have a method, a bunch of parameters, an ID so that you can map results back to the message you sent, and then a result parameter. So the purpose of the Stratum is to get the constraints from the pool for your block headers. And basically the idea with mining, if you're not familiar, is you're trying to create as many valid variations in the header. Because each time you change the header, you hash it to see if you get a golden nonce, or you win the block, basically. With that, you also send back your shares that are good enough to get rewards. And yeah, there's a whole bunch of messages. I'll go through them as well here. The basic process for Stratum is you connect, you configure. Basically, you tell the pool you support version rolling. So I'll go through that in a minute here. You subscribe. Basically, you tell them you're going to do some mining and you're a Bitaxe. They will give you back a unique identifier that you'll use to generate your headers, as well as information about how much extra space you have to modify this extra nonce portion of the header. After that, you give them your wallet address and your name, and then you loop on these 2 things, basically. You listen for new jobs coming in. You check from the pool if they change the difficulty level on you, and the difficulty level is the threshold for your result that's good enough, that the pool will accept and give you rewards for. And then you submit your shares through mining.submit. Okay, and this is what it looks like in ESP Miner. Config, subscribe, auth, and then you receive messages and process them. The mining.notify. Yeah, this is the really dirty work here. But these are all of the parameters that the pool gives you in order to construct those block headers. So I'll try my best to walk through this, but it's always very confusing, especially with the order it's in and NDNS. But basically, the mining notify has a job ID that you'll use to submit work. It has the previous block hash of the header. It has parts of the Coinbase, and the Coinbase is where you're going to make modifications to create a new header, block header. And then it has a couple of other constants for you to insert into the header. Additionally, it has this clean job flag that tells you if you need to reset your work queue because a new block came in, everything that you were doing no longer matters. So when you see this, you clean out what you're doing and force it to update the work. And ESP Miner is responsible for parsing it and queuing it into the work queue. So this is the mining part, at least from the controller's point of view. You're going to create a unique Coinbase and Merkle root so that you have a unique block header to do work on. And the way that works is the stratum gives you one chunk of the Coinbase as well as the end chunk of the Coinbase. And in the middle, you have your unique identifier it gave you, and then you can change this to whatever you want to generate more work. So it gives you space to create new unique headers to do work on. And so then you hash it and do the Merkle branch walk up to create your Merkle root. And it looks like this. You have your new Coinbase, hash it with each branch that the mining.notify gave you, and you have your new Merkle root. This is what it looks like in ESP Miner in the mining.c module. Construct the Coinbase, do the Merkle root walk up. And this is the whole generate work. So it'll create your magic number inside the Coinbase, constructs a new Coinbase, calculate the Merkle root, and then build a hash or a header that you can then give to your ASIC. So now you have all of this, all the parts of the header, and you're ready to send this work to the ASIC. This is what the bitmain UART commands look like. And this is again from Nebula's amazing BM 1397 datasheet. You have some magic bytes here to start the frame. You have some bits here to determine the type of data you're sending. So you can send jobs, you can send special commands, and there's broadcast and unicast messaging to the ASIC. The main one we're interested in is sending a job to all chips. And this is the data that you will package in and ship over that UART to the ASIC, so then it can start doing work. And this is the struct, the unique job ID. This is for you to map back to your data, so then you can reconstruct the header from the ASIC. But you have your Merkle root, the previous block hash, the base version, and all the other constants in the header. And this is what it looks like shipping it off to the ASIC. You copy over the struct into that data frame, and then you send it over UART with all those flags that are defined in that frame. And then the ASIC does its magic. So what it does internally, it goes over the non-space. So it goes from 0 all the way to the end, hashes it all, tries to find one that matches your configured target. It also, the newer ones, iterate over the version. And there's actually a BIP 320 that defines the extra space in the version field of the header that lets miners hash over that range as well. And that's important because this space actually isn't very big for how fast these miners are now. You actually need way more bits now, so you don't bottleneck the miner. Without that, you'll end up sending a ton more work or having to refresh the work because these miners are so fast now. And yeah, like I said, for each version in nonce, it does the full SHA-256 hash, checks the difficulty target, and then returns results back to your controller. And this is what the return format looks like. So the controller will be sitting there listening. It'll be watching for this frame over the RX pin. And with it, you'll get the nonce value it found that was good, a job ID, so you can map back to your Merkle root that you built. Mid-state's not really important here. That's an artifact of an older protocol. And then the version bits that it rolled over. And you'll combine this version bits with the version that was provided by the pool into a new version field to make your new block header. So you like I said, you retrieve the extra nonce that you have stored and saved using the job ID that the ASIC gave you. With that, you can rebuild the hash. You want to double check that the nonce it gave you was actually good and it wasn't a part of some kind of error. So you make sure it meets the pool's minimum difficulty and validate that it's legitimate. And then you do the mining.submit back up to the pool. What's required is your identifiers, the extra nonce 2 that you used, your extra magic number that you use to create the Merkle root. You need the time, the nonce, and then the version. And then the pool can take all this, reconstruct the header based on what it knows, and decide if your share is valid, and you get rewards. So this is what it looks like in ESP Miner. Let's see. Yeah, there's this defined function that reads from the UART. It gets that frame, tests the nonce value from the frame, and then builds the share. So to summarize, this is the main steps of Bitcoin mining controller. You initialize the hardware. You monitor the fan, the power. You connect to the stratum. You convert the stratum messages into work for the ASIC. And then you send the work back up, or sorry, you send the work to the ASIC for it to run through the nonce and version space. You wait and listen for nonces from the chip, and then you send results back up to the pool. And as a reminder, this is kind of what it all looks like. The control board sends the messages to the ASICs. The power management task, whatever it is, monitors the fans and checks the voltage and power to the ASICs. So that's it. That's sort of the high level about how you write Bitcoin mining firmware. Of course, once you get into the details, it gets really complicated. But at the very least, with this information, you'll be able to hopefully look at the code base and be able to identify keywords and start to at least know what questions to ask your LLM, basically. With that, in my mind, these are some cool things that I hope come to ESP Miner, and I suspect they will. With our current sort of power management thread is very simple. It doesn't really do a lot of fine tuning. And we've seen some hints of contributors playing with this, so I suspect that soon we'll have advanced auto tuning. Maybe not quite what Brains does, but hopefully we'll get some hackers figuring out a control algorithm to sort of find optimal settings. Whether that's you lock the fan and you try to find the optimal frequency that fan can support, or you blast the fan all the way and find the optimal hash rate for your specific chip. as Scott showed, we're definitely going to have some new ASICs coming. It takes a while to uncover all the dirty details of talking to these things. But Scott showed hints of Block, Intel, and there's, I think there's another dev that's funded that's working on What's Miner. So hopefully that comes soon. I believe that's not too different from the Bitmain chips in that I'm pretty sure it uses a regular 8-bit UART, which is nice. And then, of course, there'll be more hardware configurations, whether that's more multi-chip, for sure. Personally, one thing I would love to see is sort of a version of a Bitaxe that can drive an entire hash board. The funny thing is with version rolling, that these microcontrollers, from my math, can actually drive about 100 ASICs, which is roughly a full hash board. So in my mind, that's sort of like the max that this ESP miner can do in terms of hash rate. And so that would put it at a single hash board, you can do almost 1,000 watts and anywhere from 30 to 50 terahash per second. So I think that would be really cool. That's something I've always wanted to see happen. So hopefully that's something that can be hacked together. So yeah, I would also like to thank all the contributors, Scott, Wanklu, Nebula, Eric, Mutatram, all these guys that just came out of nowhere and have turned this little prototype into like an amazing product. It's kind of unbelievable. I would have never guessed it got this big so fast. So it's really exciting. And it's really cool to see the power of open source software. You just release something, it's cool, and then a year later, it's all over the world. Chinese clones are coming out. That was actually one of my favorite things, was seeing an actual Chinese clone. I thought that was awesome. But yeah, really proud of this, and excited to see what happens with this open source mining stuff. There's definitely a huge opportunity for whoever cracks the industry grade open source mining platform, because there's a lot of fees those mining firmwares collect. So I suspect that that'll be a big deal, and it will come. These LLMs and ChatGPT, the things you can learn and do are unbelievable, especially with open software. So yeah, for more resources, like I said, here's the data sheet for the Bitmain chip. This is where you can find ESP Miner, and check out the OSMU wiki for information on all the OSMU projects. Thank you.
Johnny, thank you for that very, very basic walkthrough. Appreciate that. Have you looked into the SV2 firmware, and what are the primary differences?
I don't know. Me? I don't know anything about SV2, to be honest.
Oh, I have a zine for you then. Where are these ASICs coming from? Are they all coming from old machines?
No, there's a big supply for repair. So they do manufacture these things for repair purposes. So some people get them from that. I mean, I'm not an expert. I don't know
awesome.
all of it. You might even be able to get them directly now, right? Is that right? Okay.
So how many ASIC chips are in a hash board?
Like 100.
And how many hash boards are on like a new miner?
There's 3. Yeah.
Okay.
So you get 300.
Oh, that's pretty good. Okay. Thank you.
Yeah, it's pretty labor intensive too to extract them. So yeah, we'll see what happens.
It's not like a sustainable process.
No.
Like, this is not how legitimate electronics are made. So that's why we're very excited about willing manufacturers like, Intel previously was, Block, and potentially new partners to have like to have a manufacturing partner that isn't like this adversarial relationship would really help.
Yeah, that's what I was wondering, if it could be profitable for, possibly not Bitmain, but for the other manufacturers to get involved. That'd be cool.
Yeah.
I think so. I think it's coming around. I think that as this project grows, they're starting to pay attention. And I've had some like feelers. They're still like, well, it's a pretty small market, but there's potential.
I do think like to get home miners to that like 1,000-watt level, I do think the easiest way is just to recycle these old hash boards, because they get quite cheap, like 1 or 2 years later, and they're quite cheap. And you get 100 ASICs and it can do 1,000 watts. It's pretty intense.
Can you guys describe the process of reverse engineering? I guess
that would be a whole talk, but I'll try.
If there's such thing as a brief version of that.
Well, yeah, I'll try to explain it. Actually, this is like my favorite part. It's like a crazy puzzle that you're trying to find the secrets, but you do a lot of tricks. You'll hook up what's called the logic analyzer that can watch the signal and convert it into something that you can read on your computer. And then there's tools to like split up all the bits that you got and make it readable, so you can actually look at it like UART frames, and then you can start to piece together what it means. And actually, Nebula did a lot of work creating one of these tools where you can take the serial message from a Bitmain machine, put it in this tool, and you'll be able to read all of the frames. And so that's really helpful. You can also, at least the older Bitmain firmware, you can download it straight from their website, put it through a tool called Geardra, which will decompile the code. And then you can feed the decompiled code into an LLM, and it'll help you understand what they're doing. So you get a combination of source code or decompiled code. You get these logic analyzer to see actual data that's going between the chips. And then you can also do things like set up a fake Stratum server, have the miner connect to the fake Stratum server, so you know exactly what the header is they used and all the like extra nonce bits, so that when you see the frame come across, you know exactly what is what, so then you can piece it all together. So you can do a bit of black box reverse engineering like that, logic analyzer, and source code and decompiling.
Very cool.
Yeah.
So you mentioned about that extra nonce that we can do. So I am assuming this extra nonce is just like integer or something, like, or long numbers are there. But I read that we can change the dates also and something to get the right hash.
Yeah. So the Bitmain chips do version and nonce. Some of these other chips we're learning also do end time. So you have like a big range of time, like 2 hours or whatever, for, I don't know, something like that. But you can change a couple of bits and you're safe. You're not going to be outside the valid range. So some of these ASICs do it. The Intel ASIC will do like 3 bits or 2 bits, somewhere in there, of the end time to give you a little bit more. So yeah, some of the chips do that.
Okay, so the different ASICs have the different capabilities.
Yeah, that's right. I suspect all of the newer ones will have all 3 because they're going to get increasingly fast. So.
Do you guys have any guesses about why Bitmain is so adversarial? Like, it seems like it would be not in their best interest to not be open. Like,
no, I think it is in their best interest.
Why?
Because, well, okay, my perspective is this is going to commoditize at some point. You're already seeing diminishing returns. It'll eventually commoditize. And until then, they need to keep their IP as secret as possible and extract the profit until everyone else catches up.
Are they worried about like other people coming up with like competing like fabs, like to fab competing chips, or is it like they don't want you existing because they want to sell the whole package? And
I don't think they care about us. They just want to make sure that no one can compete with them, and so they'll do everything they can to try to keep it.
Like, I assume that most of the like Bitmain's value that they capture is on the chips. Or maybe is that not true? Or
I suspect they consider everything a part of it. So I don't know.
Okay.
Yeah, I think it's just pure competitive profit, and I suspect their window is going to close at some point. So
Okay, thank you.
But again, we don't know. I don't know anyone that actually has ever talked to Bitmain.
Have you taken a look at the proto chips?
Scott has. They're cool. You'll see it eventually.
Data sheets?
Maybe. Maybe. Yeah. Yeah.
They have data sheets, and I've actually talked with a couple ASIC manufacturers, but these guys, they don't really have like open source brains. So unfortunately, I have to sign NDAs to get these data sheets, which is really disappointing. But I tell them, like, if that means I can't release an open source miner based on your design, like, that's a non-starter. Forget about it. And so they're all kind of like, all right, well, you sign this NDA to get the data sheet, but you can't release the data sheet directly, but you can release a design that you've made based on that data. So that's kind of where they're at. I think this is just like, we're early.
Yeah, there's still NDAs. I've signed an NDA for one of these, and it's still awkward.
Any other questions? All right, let's put our hands together for Johnny.
Super well done. That was such a high level overview of your work. Really appreciated it. What if people, Johnny, if people want to, Josh, if you want to come up and figure out, start getting connected. If people want to, like, if they're interested in contributing or participating, is there like sorry, maybe I should ask you while you're up here. Is there like, what's the best way for people to get involved? Is it just run a miner? OSMU.org or .net or .com?
I think it's OSU.wiki, and then you can find the Discord and everything.
Cool.
Yeah. Yeah, the Discord's crazy. There's like 10,000 people in there or something.
Holy cow.
It's
Is there
amazing.
any particular type of work you're looking for or help that you guys are like skill sets that you're like, we really need a...
I don't know, because like one of the biggest contributors was a web dev, and I would have never guessed that. It's just anyone that's interested. It's really about like having a tolerance and interest in it.
Cool.
Yeah.
Great.